So opening your notes to page 54, we're going to do higher order derivatives because when we're talking about our physics stuff, and we call it particle motion, we have position, velocity, and acceleration. And velocity and acceleration are derivatives. Acceleration is the derivative of velocity, which is the derivative of position. So we get multiple derivatives going on. I want to make sure you're comfortable with the notation. This column we're not going to do. That's old-fashioned notation that I haven't seen for years, but we'll get familiar with the others. Honestly, in this class, for our purposes, we rarely, if ever, go beyond a second derivative, but know that they do exist, and in higher levels, we do go farther. In Calc 2, we end up going sometimes up to a fifth or sixth derivative when we're doing something with series work. And in physics, you can go beyond a second derivative because the derivative of acceleration is jerk. It tells you how fast your acceleration is changing. So if it's not, you have a nice smooth ride. But if you're hitting the accelerator and the brake and that's causing you to jerk, that's a third derivative. So first derivative, when the function's written as y equals, we can call it y prime, y double prime, y triple prime. Once it gets past three of them, they'll put a number up there. So for example, the sixth derivative, it would say y and it'd have a little 6 right there. Doesn't mean to the sixth power, it means the sixth derivative. So notation. The other way you'll see it when they write it in the form y equals is called in Leibniz notation. It's a little bit more formal, but it's going to be our big winner eventually. We write this as dy dx. The reason this is going to be used more is because this tells you what's changing over what unit. So when I write dv dt, that means how is the volume changing over time if something's leaking. And so that's actually the more applicable form. The second derivative of that looks like dy squared. It's a little 2, it's actually not squared, over d squared x. It looks like that. And likewise, the third derivative would have 3's. We'll just stop at the second derivative. The other way is if it's written as f of x equals, just like you've been used to, we write it as f prime of x and f double prime of x and triple prime and nth prime. You got the gist of it. I can hardly reach over there. Last up is sometimes if it's written as f of x equals, and then there's some function, like maybe the original function was sine x or e to the x or something, sometimes they'll write it like this. Take the derivative of, and it'll, like if f was sine, it'll say d sine x dx. That just means take the derivative of that function. If they want you to take the second derivative, it will again be in this notation. It'll be f of x, and I'll have a little 2, and then it'll look like that. All right, so that's just notation. They're easy to take. We're not going to focus a whole lot on our, see, now that recorded. Sorry about that. I'm on a leash if you're watching the video. You don't need, I'm not on a leash, I'm, whatever. Always happens. Anyway, so we're not going to really do like second and third derivatives of basic functions. We're going to put them more in the context of physics. But when this says find all the derivatives, I'd say no way, Jose. You know, I'm not going to do that. But I'll start for you. I would do the first derivative by just using my power rule. It'll be nice and easy, and I'm done. That's the first derivative. Then I could do the second derivative by taking the derivative of the first derivative. Nice and easy. Power rule again. 126 x to the fifth, and then what would that be? 84 x squared. And it doesn't get more difficult. It just gets a little bit more annoying, right? But I could continue. What will this polynomial function eventually be if I take all of its derivatives? 0. Polynomial functions eventually always go to 0. Some other functions never go to 0 when you take their derivatives, like sine. You know what I mean? That's going to go sine, negative cosine, negative sine. It's going to keep cycling. What that does in higher levels of math, too, is we have what's called kind of the hierarchy of functions, like who grows the fastest, who grows the slowest, and that kind of stuff. And polynomial functions are pretty weak because of the fact that their derivatives go to 0. You'll get into that more later. So we're going to put this in our particle motion arena here. We've already talked about how velocity is the derivative of position. So let's write that over here. Velocity is the change in position over change in time. Sometimes we'll write that delta x over delta t. Depends on what texts you're using. But really, if I want to know at this instant, then that change in time is approaching zero. And really what I get is the derivative of position. And I just take a derivative. So velocity is the derivative of position. We write it like this, which I've already told you this part. So this is old news. We write it like that. If I want to know what's the velocity at 7 seconds into some movement, take the derivative and plug in a 7. It's as easy as that. However, acceleration is the derivative of velocity. It's the rate of change of velocity. And that's what a derivative is, by the way. It's always a rate of change. It adds the word per. So instead of having change in position, we're going to have change in velocity, like feet per second, over change in time, which gives you feet per second per second. Every time I say per, that's a derivative. So this is the derivative of velocity. How do I write that with notation? I would write it like this. The acceleration at any time t can be found by taking the derivative of the velocity function, which could also be done by taking the second derivative of position. So that's all saying the same stuff. What I'd like you to do is on the side go like this, SVA. You're going to be writing that quite a bit. Because right now we're just taking derivatives, so I want you to write an arrow and go like that. Given the position function, to get to acceleration, we do derivative and another derivative. We are eventually later, don't draw this, going to work up, and we're going to have a process called integration that's going to allow you to go from acceleration back to velocity, which is kind of cool, but we don't know that till chapter 4. So we're just going to be taking derivatives. And keep in mind, what did we say last week that speed is? Speed's the what? There it is. Yeah, absolute value of velocity. Velocity. All right, so we would write that as speed. There is no abbreviation for it. You might say it's S. S is actually position. Sometimes that's called R for rate, but speed is actually the absolute value of your velocity function. So if velocity is negative 30, your speed is 30 miles per hour, you're just going backwards. So it says also important, and this is big, it's got a star here because this is an AP favorite. They love to ask you when the speed of something's increasing or when it's decreasing. Basically, when are you going faster or when are you slowing up? There's a couple things that affect that. In order for your speed to be increasing, you have to actually analyze two things. So right when, you have to look at velocity. Do you think it has to be positive or negative? It's a trick question. It can be either. Yeah, you can be speeding up and going backwards, right? That's you're backing out of your driveway and you know what I mean, you go faster and faster. You can also be speeding up going forward. So the sign of this has nothing to do with how fast you're moving, it just gives direction. So it's when the velocity, and then we also have to look at acceleration. And we have to tore the tip off of this. Oh, I'm recording, I forgot again. Okay, anyway. When velocity and acceleration are. And I want you to write when they're the same sign, and then we'll discuss what that means. So we need when the velocity and the acceleration are either both positive. And I'm going to discuss that scenario. That's the one that's super common sense. If your velocity is positive, you're going forward. If your acceleration is positive, your velocity is increasing, right? So what that means is you're gunning it forward. That's you driving and you're going from 30 miles an hour to 40 miles per hour to 50 miles per hour. You're going forward faster and faster. That makes sense. But it's also possible for you to speed up in this scenario. Now, that one's a little harder one to explain, but how about like something being dropped off the building? If I drop something off the building, its velocity is negative because it's going down, correct? And acceleration due to gravity is negative 9.8 meters per second, right? So you have both of them being negative. And isn't the speed increasing as it's falling? So that's kind of an example of that. So you analyze the signs. If they're the same, you're getting faster. If they run at counter purposes, that's you putting on your brakes when you get to a stop sign. You're still going forward, right? But slower. And so if they run at 1 plus, 1 minus, you will slow down. So how do you decide when that's happening, when all they do, you don't have a calculator, you can't graph it, all they do is give you some algebraic model that represents the scenario. This is what you do. I'm going to have you do a little fake one here. You make what I call a velocity sine line. And it's going to represent the velocity at any time. So you might even want to write v of t. Time can never be below 0. We're not going to go back in time. What you do is you figure out where is the velocity 0. That'll be easy. So you're going to have some model and you're going to say, well, where's the velocity is 0? And suppose you figure out that happened at 2 seconds and 6 seconds. What does that mean the particle's doing? If the velocity is 0, what's the situation? So that's a good question. If velocity is 0 at 2 seconds, what's happening at 2 seconds? It's either stopped, well, it's totally stopped, and it either can stop, let's do this, and continue to go forward or continue to go in the same direction, or it could be stopped and change directions. And that's important. Just because a particle is stopped does not mean it changed directions. This scenario right here at 2 seconds, you were going forward, you stopped, you continued to go forward, you stopped, and then you went backward. Does that make sense? So now let's say you did the acceleration, you did the same thing, and you figured out that at 5 had no acceleration. By the way, real world wise, what does it mean if acceleration is 0? Does it mean you've stopped? Right, you are going constant speed. You can even think of that as slope. The tangent line would be horizontal, but it really just means you're on cruise control. Let's suppose that this one went minus plus. There is just one small time frame in there where the particle is speeding up. Can you find it? There's one small little time period where that thing was speeding up. Otherwise, it's pretty much slowing down the whole time. Where was it speeding up? From 5 to 6. Why? Yeah, because they're both positive. They aren't both negative anywhere. But right here, we've got an issue. We're going forward, but our acceleration is negative, which means we have the brakes on. Okay, that's what's happening. Once I get to 5, between 5 and 6, both are positive. So I would say the speed is increasing on the interval 5 to 6. It's decreasing everywhere else. You got it? All right, so that's it for the notes. Now, if you're listening to the video because you were gone on Thursday, you're going to have to take out a blank sheet of paper because I handed them out a sheet of paper that looks like this, and it's super important because on the bottom of it, it says, this is so important that tomorrow you will be getting a quiz on it. Okay, so tomorrow there's a quiz. I'm going to give you one just like this. Not only is it going to be super similar, but it's the exact one on page 56 in your notes. It's the exact one. If you go to page 56, look at it. Do you see there's a particle motion problem? The big old honking star by it? I'm going to have that be one of your 3 quiz questions tomorrow, and I videoed the solution. So if you watch it, there's no way you can't ace that. It's going to be 2 points per part, so 10 points for that question. There's going to be one other question, which I also discuss in the video, so if you watch it, you've got 2 of them. The third question, I stole off the homework of 2.2 just to keep you honest. Okay, it was towards the end, and some people, once they get to the end, they copy out of the back. Not everybody, a couple. So you will have a quiz tomorrow, one very similar to this, and I'm giving you it actually in that video. So if you watch that, you'll be great. You might not need to watch it because you might be like, I got it. Fine. So once we're done with this, we will quit for the day. I'm giving you the position of a particle moving along the x-axis. What they're telling you is that it's moving horizontally. If they say along the y-axis, then we're moving vertically. If you're moving a mixture of those, like you're kind of going all over the place, that's Calc 2. That's called parametric motion, and that we need a little higher level. So in Calc 1, we are either moving left, right, or up, down. Pretty straightforward. This says when, so I'm looking for a time interval, does the particle change direction? That's a question actually about velocity, because when you change direction, what's your velocity going to be? 0. So I'm actually looking not only for where the velocity equals 0, but it also has to change signs. So that's important. But to figure out that sign change, I have to, it's kind of like that intermediate value theorem. If it changes signs, it must have hit 0. But the reverse is true too. So I'm looking for v of t to change signs. In order for me to figure that out, I need to make what I call a velocity sign line. In order for me to do that, I need the velocity function. So I need to take the derivative of position, and it'll be nice and easy and algebraic for now. That would be 3t squared, using my power rule, minus 24t plus 21. I'm in search of where the velocity is 0 because that will tell me when it's stopped. I'll decide whether it stopped and went forward or changed directions once I'm done. If you don't have a calculator, it'll factor super easy. If you have a calculator, then we can go calc 0, but these are usually non-calculator active. So we're just going to factor this nice and easy. It'll be nice, easy, quadratic. So my velocity model is 3 times t minus 1 times t minus 7. That will give me the velocity instantaneously at any time. It's 0 at 1, so go put a 1 right here, and a 7. The velocity is 0. That indicates one of two things. For sure, the particle has stopped, but I have to decide whether it stopped and reversed itself, because this says change direction. This is how you decide it. Each one of these intervals, you have to have the entire same sign. So between 1 and 7, it's either all negative or all positive, because if there was a change, there would have been another 0 in there. Does that make sense? So I really just test my favorite numbers in each interval, and I test them in the factored version of my velocity, because I don't care about the number, I'm caring about the sign, because I need to change direction. So I'm going to pick my favorite number in here, 1/2, and I'm going to pretend I'm plugging it in right here for t, and I'm only going to look at signs. I would have a positive times a negative times a negative if I put in a 1/2. So this is positive. What does that mean the particle's doing? For the first second or minute or whatever the unit of time is, it's going forward. Does that make sense? All right, then I'm going to pick my favorite number in this time interval, maybe 4. Pick anything, and I'm going to plug it in, and I'm going to look at the signs. It would be a 3, right, times a positive times a negative. I don't care what it is. I just want to know if it's going forwards or backwards. And likewise, if I pick my favorite number to the right of 7, like 10, it's all going to be positive. That tells me the movement of the particle. It went forward for a second, reversed directions, went backwards for 6 seconds, and then went forward on out to infinity. The question was, when does it change direction? And this is definitely a change in direction at 1 and at 7. However, just for the heck of it, don't write this on your notes. Had that been plus and then minus, then there was only one change in direction, and that would have been at 7 seconds. All right, when is it moving to the left? Well, that comes from my velocity again. The sign of your velocity gives you your movement. It would have been moving to the left when v of t was negative. That happened on the interval from 1 to 7. Done. The next question actually comes from a few days ago. I threw it in there as an extra. It says average velocity. I don't want to know at any particular time. I want to know its average from 1 to 2. How do we figure out our average velocity from last week? What do I just do? Yes, I average it out. It's like the slope of the secant line. It's just change in position over change in time. So I figure out my position at the end of the time interval. I figure out my position at the beginning. I plug them into the position function to see how far I moved. Maybe it was 8. I don't know. I'm not going to do the arithmetic. And then I say, well, that was over 1 second. And that'll give me my average feet per second on that interval. Okay, I'm not going to do them. You can do the arithmetic. When it says what is the velocity, not average, at this particular time, you just plug 4 into your velocity model. So I'm just asking you, what is v of 4? Now go back up to your velocity model. Is it going to be easiest to plug that 4 into the quadratic or into the factored version? What I'm saying is, should I plug it into here or should I plug it into here? If you don't have a calculator, who's going to be less dangerous? Factored. Yeah, so take advantage of that because you usually will, this part of your exam is no calculator, the whole particle motion page. So make sure you make your arithmetic easier. I'm just going to pretend I'm sticking in a 4 for t. I'd have 3 times 3 times negative 3. It's going to be a negative 27. Let's go right there. I knew it'd be negative, by the way, because my velocity sign line was negative from 1 to 4. Negative 27. That means it was going backwards at 27 whatevers per whatever. When is the speed increasing? All right. To decide when the speed is increasing, I have to analyze two things. I need my velocity and acceleration to be both positive, I'm gunning it forward, or both negative, gunning it in reverse. I already have my velocity mapped out, so let's go put that on here because we have to look at them simultaneously. So I already know that it was stopped at 1. It was stopped at 7, and it was going forwards, backwards, forwards. That I already did. The next thing I need to do, though, is also at the same time look at how it's accelerating. So you need to go off to the side, and you need to figure out what your acceleration model is. How am I going to figure that out? Derivative. So go back to your velocity model and take its derivative. I remember it was 3t squared, so it's 6t. Can you tell me what the next thing would be? If minus 24, perfect. Now, in order for me to figure out the signs, because I'm going to make this sign line, I need to find the zeros. That one's so easy. It was obviously 0 at 4, so go put a 4 here. Acceleration was 0. What that means is that 4 seconds in, the cruise control was set. It doesn't mean it stopped. Right? So now I'm just going to run a little test. I'm going to pick my favorite number to the left of 4, maybe 2, and I'm going to easily see that the acceleration was negative. And then over here, the acceleration was positive if you put in like a 10. Now I can answer the question, is there any time interval where I was gunning it forward and thus my speed was increasing? So I'm looking for positives on both sign lines. There is. Where is it? After 7. So we would say on 7, make sure it's open because at 7 you were stopped. That's a detail that's actually important. So 7 to infinity, I had the pedal to the metal going forward. Is there anywhere else where I was in reverse with the pedal to the metal? Yeah, between 1 and 4, both are negative. So you'd say 1, 4, union 7, infinity. Now, if that is a decreasing, I'd pick at where they had opposite signs. And what that means is your brakes are on, but you're going forward. So you would be slowing down. What do you think? Got it? It's pretty straightforward. The math, and it's easy. I'm not really concerned about the math. It's understanding what's going on. So you're going to take a quiz on this tomorrow. There's 3 questions. The problem on page 56, which I videoed, so if you want to watch that to make sure you ace it, it's a 10-point problem. Then there's going to be also a graph that you're going to interpret, but I do one like it in the video, so you'll make sure you ace those. And then the third is off the homework you turned in yesterday. You don't know what that is. Okay, so it'll be, and I think it adds up to like 15 or 16 points. So a pretty big quiz, but it won't take you long. All right, so worksheet is what we're going to work on. If you could take that out, did I pass it out yet? I didn't. Here, pass these out because I'm still tied to my leash. Yeah, I am because I'm going to stop it actually because